Hello, everyone. My name is Beata Kenik. I am from Viga Foundation from Poland, and today I have a huge pleasure and honor to talk with Professor Roger Penrose, an outstanding British mathematician, mathematical physicist, philosopher of science, the winner of the Nobel Prize in Physics in 2020 for the discovery that black hole formation is a robust prediction of the general theory of relativity. In a trembling voice, good afternoon, Professor Penrose. Thank you so much for joining me today.
Hello, it's my pleasure.
Professor Penrose, I would like to start with black holes. Historically speaking, the idea that there might exist objects from which even light is unable to escape was proposed quite a long time ago, at the end of the 18th century, if I'm not mistaken. Yet for more than 1.5 centuries, it wasn't generally accepted. Albert Einstein seriously doubted, to say the least, the existence of black holes. And then in 1964, you wrote a breakthrough paper in which you proposed mathematical tools to describe black holes as objects predicted by Einstein's theory of relativity. Could you please tell us, in layman's terms, a little more about it? Well, in what way does the general theory of relativity predict the existence of black holes?
I think perhaps I should slightly correct the history. I know what you said is very much what people think, but the work done by John Michell, which was using Newtonian theory, and in a certain sense, it's not really correct. You see, the thing is, he argued that if you have a large enough body, massive enough body, then the escape velocity will be greater than the speed of light, so that you would have to travel faster than light to escape. There's a sort of velocity known as the escape velocity, which is the speed you have to get to in order to leave a planet or a body completely. The trouble is that you don't know what the speed of light is. See, in Newtonian theory, the speed of light is not really a constant. You see, you have to assume. The problem I have with the original Mitchell argument is that if you take light coming from a long distance, falling on this large body, and you had a mirror, it would reflect back out again and escape. And so it's not really dark. I don't really want to go into that. It's just this, I mean, it was an impressive piece of work he did, but it doesn't really have the correct prediction of a black hole. You have to go to Einstein's theory. And Einstein's theory, there the speed of light is definitely a fixed number. And you have this feature that light can't come in and bounce off because it gets swallowed. You're right in saying that Einstein would probably have been extremely skeptical of black holes and certainly made arguments against such things, trying to say that they wouldn't happen, basically. There was an important paper just before the war by Oppenheimer and Snyder, where they considered that 1939, this is before Oppenheimer worked on the atomic bomb and things like that, but he did work on general relativity. And they had a model which was within the proper Einstein picture, and you can have collapsing dust cloud it was. And dust means you have material with no pressure. That's not really realistic because material does have pressure. But the main point was that it was symmetrical. So everything falls in. There's no pressure, nothing to stop it. And so as it falls inwards, it will fall in towards the center, and the densities will get larger and larger and become infinite as everything falls towards this one point. Now, that's not realistic, as many people argued, because there would be irregularities. Of course, it would have pressure, but the important thing is you'd have irregularities. So it wouldn't necessarily meet in a point. It would swish round and come swirling out again. And I think that was the picture normally people had, that it wouldn't, because it's very unrealistic to have this very exact symmetrical situation. So I produced arguments where you show that actually it can be as irregular as you like, as long as it satisfies a certain condition, which I called a trapped surface occurring, which really meant that light, it had to do with the focusing of light coming from a body. And I studied what would happen to the future of an object. And this would be this collapsing body, and you imagine a sphere surrounding the body, and if the light from that sphere would be focusing inwards, I mean, a flash of light on that sphere, what you expect would be focusing inward, but would get smaller. But the point is that when you get inside this horizon, as we call it, the light going outwards would also be getting smaller. And you could show by using I had to develop mathematical techniques, which were not what people were using at the time. People either used exact solutions, you see, but if you have irregularity, you couldn't find an exact solution. Or you would put things on computers. And in those days, well, computers were nowhere good enough. Even now, you couldn't really tell you get a singularity, which is when the density becomes infinite and the curvatures become infinite. This would not be something you could really tell with a computer calculation either, because it would just, you say, oh, my computer's run out of memory, or it's something that's gone out of the range that the computer is capable of dealing with, but it's not realistic, you might argue. But this was a mathematical argument which showed if the energy never became negative, that was a key point. If the local energy flux across a surface never becomes negative, then you would necessarily have these singularities. It's actually not quite true what is said in the Nobel citation, because what they say is, I can understand why they say it that way, but what they say is that the black holes are a robust prediction of the general theory of relativity. What I showed was a robust prediction was really the production of singularities. So this means a place where things go wrong. You have infinite curvatures or infinite densities or something crazy. What gives you the black hole is that these places where you have infinite densities, infinite curvatures, are not visible from the outside. And even now, I think there is no argument in favor of what I used to call cosmic censorship, that somehow there is a censor. You can't see these singular states, and that's what a black hole gives you, something where you have inside it the place where things go crazy, but you can't actually see that. It's not proved, as far as I know, even now, that you couldn't have a situation where it would collapse to a visible singularity, what you used to call a naked singularity. I don't believe you could have such things in general collapse, but as a mathematical statement, I don't think there is even now a proof that they don't happen in general.
Before I, of course, come back to black holes, I would like to mention, if I may, a conference which took place near Warsaw in the palace in Jabłonna in 1962. You were there, right? With an impressive number of iconic scientists like Richard Feynman, Paul Dirac. And I understand, okay, the topic of the conference was the theory of gravity. And correct me if I'm wrong, but even at that time, black holes were not quite taken quite seriously by scientists. I mean, I'm not sure if I'm using the correct phrasing.
That was before my result, wasn't it? That was, well, I proved my thing in 1964. The publication was 65. But I gave a lecture in London on it in 1964. Yes, the conference in Jabłonna was before that. And certainly I don't think we were talking about things like black holes at all. I can't remember them being discussed there. I remember talking to Feynman, certainly, on occasion. That was one of my interesting encounters with him. And I
was curious. I was curious about that.
About Feynman. Yeah, well, I had a very interesting encounter with him. Well, there were two. One was I had a private discussion with him about something quite different. This had to do with his picture of zigzags and whether you could. Let's not go into that. That's a different topic. But I was there with my then wife, and we'd driven there by car. And at the end of the conference, people were going to a meeting in Zakopane, in the mountains, and since we didn't want to go in the coach, we wanted to go, but we didn't want to go in the coach. And so we tried to find out where the meeting would be in Zakopane, and they wouldn't tell us. They refused to say anything at the conference desk. And so we told Feynman about this. He said, "Oh, I'll find out for you." See? And so I had no idea what he did, but I was about to leave, I remember, in the car, and Feynman came up, and there was a little folded up piece of paper saying Agent X4 or something like this, and inside was the name of the hotel. So somehow he had managed to find out what the name of the hotel was. The curious thing was, it was nothing to do with, I don't know, security or anything like that. We found out what it was. It was that people at the conference were being charged double the price of an ordinary person. And they didn't want to let on. So when we went there, we were charged only half the price of anybody else. But that was an interesting.
So tell me, what is, coming back to black holes, what's characteristic about black holes? How do scientists detect them? I know it's very difficult for non-experts, including me, to understand the mathematical complexity. But generally speaking, how do scientists detect them? Because of course there is no doubt today that they do exist. They are there, and they are observed somehow.
Well, you see, you don't really see them in the sense of, you see, the whole point about a black hole is that you have a thing called a horizon. This is where light, it's basically the argument I was using at the beginning. You see, you have a flash of light, and you could imagine a surface, and the light flashes from that surface on both sides. And you imagine if it's curved inwards like this, then they'd converge on that side and diverge on the other side. But inside a black hole, they converge on both sides. This roughly means that if you get to a point where this convergence becomes just parallel, and that's what you call the horizon. If it's inside, light can't escape. But when you're on the horizon, light just can mark time. It's really not very easy to understand these things without drawing four-dimensional pictures. You see, you have to draw pictures of the cones, which represent how light can go. So you have a thing called a light cone. You have time in that direction and then space in these directions. And you think of a cone, I'm using two fingers here, but you imagine you rotate these fingers round to make a cone. Then a massive particle's world line, that's history, must be within the cone. It travels less than the speed of light. Light itself is along the cone. Faster than light would be outside the cone. Now, these cones describe an important aspect of the geometry. Now, when you get to a black hole, they tip over so that they are vertical, and the light actually follows the outmost region of the cone. Is just staying put. It doesn't go out or it doesn't go in, it just stays there. And that's what we call the horizon. If it's further in the black hole, both sides are going in until the light can't escape. You have to understand it in these terms. Locally, there's nothing strange about it. That's what's hard to understand. Locally, the space-time is just like anywhere else. It's just that overall, the light gets trapped within this region. And when I say locally, you see, if you were in a spaceship, suppose you had a very big black hole and you happen to make a mistake and your captain had not calculated correctly, and you actually fall through this horizon, you wouldn't feel anything. There's nothing special about the horizon. It's just that the light from it doesn't manage to get outside. It would fall inwards as well. But it makes sense when you get used to these ideas, but it takes a while. But you're asking, how do people detect these things if the light can't get out? Quite right. You don't see the black hole.
Yes.
In fact, the other people who shared the black hole with me, and they did some very nice analysis independently of looking at the center of our galaxy and looking at stars. And you can see, I find it very beautiful pictures, because the black hole is so powerful that you can even track the stars going around it. My first reaction when I saw this picture is, oh, Kepler is right. because you can see the ellipses, very wonderful ellipses, and one focus of this ellipse, it's going around it. You can't see what's happening at that focus because that's the black hole. So you don't see the black hole. You see the effects of the black hole. You see all these stars going around in these different orbits. And it's an amazing picture because you can track them in real time. I mean, you have to speed up the time a bit, but I don't know I don't know how many frames. Maybe it's a month or something like that. But you could actually see them going around. And I found these pictures really incredible. And it really shows there is something there, something extremely massive, which is at the focus of all these elliptical shapes going round and round like this. It doesn't, but you don't actually see the black hole. It just looks like nothing. I think there are other photographs which you do see blackness. You don't see into it. You don't see what's, because the light can't get out. But what you do see is a black region. So there are images which look more like what you might think is a black hole, just black, because no light gets to you from that region. So yes, there are pictures like that. Not, I don't think our galaxy, there's probably an Andromeda galaxy, which has a much bigger black hole than our one.
And why are scientists, physicists, astrophysicists, mathematicians so interested in studying black holes?
Well, they're a very curious phenomenon. I mean, it's quite unlike normal physics. You see, in normal physics, you expect things to be reversible in the sense that if it happened one way, it happened the other way. And things you could bounce out again. Whereas black holes, they just go one way, and they're very curious from the point of view of physics. And you lose information, and their arguments go on endlessly about this, because some people believe you can't lose information. I think that's quite wrong. You do lose information in black holes. And I just see the arguments which try to claim that information gets back again. I just think they're wrong myself. But I shouldn't. A lot of arguments go on about that. So losing information is a phenomenon you don't have elsewhere in physics. So it's a very, very unusual kind of phenomenon. That's certainly true. So I can see why people are interested in them. And it's a feature of general relativity which you don't get in other theories. You get theories where you get singularities, but you usually think that's because you haven't taken into account some more refined consideration. And that's the only reason the singularities are not realistic. Whereas here, there seems to be no way around them. People say it's got to be quantum gravity, you see, where you combine quantum mechanics with general relativity. I don't even think that's, I mean, you would need it if you wanted to say what happens inside the black hole, but it's not much use to you because the information doesn't escape from it at all. But people argue, well, you've got the Big Bang, and that's a bit like a black hole in the other direction. But you see, it's not really. And I spent a lot of my life worrying about this whole problem because the Big Bang is not like a black hole reversed. And it's a very interesting difference. It has to do with the second law of thermodynamics and other things. I don't know if you want me to go into all that, but
well, yes, I was just going to ask you in just a moment about the theory, the Big Bang theory. Was there anything before the Big Bang? In 1964, Arno Allan Penzias and Robert Woodrow Wilson discovered the cosmic microwave background radiation.
Yeah.
And that provided another, after Edwin Hubble's discovery that the universe was expanding, argument to support the theory of the Big Bang. So I recently started reading about your reflections on what was before the Big Bang.
Well, you see, it's an interesting story. I mean, shortly after I produced my theorem, and unlike the movie, Stephen Hawking was not at the lecture I gave in London, but I did give a repeat in Cambridge where Stephen Hawking was present. And then he started working on the Big Bang issue. So he generalized the arguments I'd used so they would apply cosmological situations and produce a lot of nice results. And again, showed that the singularity in the Big Bang was a generic phenomenon. That is to say, irregularities would not give you a bounce. You could imagine a collapsing universe which swished round and come out again. But the thing is that that's not really, I used to worry about this a lot. There was another encounter I had with Feynman. I don't know what you want to say. They're always quite interesting. But I was giving a talk in Caltech about it. And I'd come to the conclusion, you see, there's one of the most, you talk about the microwave background, you see. Now, one of the most interesting observations about the microwave background, not just its discovery, which was very important, and Wilson, but the COBE satellite. This was the first of these satellites which went to look at the microwave background. And they found this very, very beautiful curve. You see, they were looking at the radiation coming from the, which was in the microwave background. It's the earliest thing we see. The earliest thing we actually directly see in the universe is the microwave background. And that is not the Big Bang. That is 380,000 years after the Big Bang. So 380,000 years. And then the radiation, see, before that time, the radiation can't really escape. It's only when it's cooled down enough that the radiation doesn't get mixed up with creations of particles and it can finally escape. And that happened 380,000 years after the Big Bang. But what they found in the COBE satellite is this beautiful curve where you plot the, in the horizontal axis, you plot the frequency, and the vertical axis, you plot the intensity, and you see this curve. And this curve fits to an extraordinary precision. You can see it well within the error bars are well within the thickness of the incline. It's an absolutely almost perfect curve, as predicted by Max Planck. Max Planck, it was the first real indication of quantum mechanics. And this showed that light comes in particles, basically. That's the sort of idea. But the main point is that you get this very particular curve when you have what is called black body radiation, which really means maximum entropy, maximum randomness. Now, you see, I regarded this as a huge paradox because you go back and back in time. We see what does the second law of thermodynamics tells you? It says that the entropy or the randomness increases with time. So the entropy goes up and up and up and up.
So entropy means going from the state of order into the state towards the state of disorder.
Disorder,
right?
yes. So it's completely random. You imagine the most random state is maximum entropy. Okay, so bear that in mind. Okay, now this was the talk I gave, which actually Feynman was present at the talk. It was quite interesting. But anyway, I was describing in that talk how, okay, you go back and back and back in time, and the entropy in forwards in time, the entropy is going up. So backwards in time, the entropy is going down. It goes down and down and down and down until you get to this microwave background. And you see this Planck curve. And the Planck curve tells you what you're looking at is a maximum entropy. You go down and down and down and down until you reach a maximum. What? I mean, it's completely crazy. Because how do you go down and down until you reach a maximum? Well, I think people thought, oh, well, the universe is expanding, so that doesn't really. But that's not the reason, because you can imagine the collapsing universe, and the entropy ought to be going up and up and up in the general collapsing universe. And so that's not what happens. What you see is this microwave background in a state of maximum entropy. The key thing, which I made in this talk in Caltech, is that the gravitational degrees of freedom were not activated. And you can understand, I like to describe it sometimes. This is an observation made by Schrödinger a long time ago, and he published a book called What is Life? See, people tend to think of, what do we get from the sun? Well, we get energy from the sun. But that's wrong. Because if we kept getting energy from the sun, we would just get hotter and hotter. Well, we are because of global warming, but I'm talking about a much bigger effect than that.
Yes.
The reason that we don't get roasted in 2 days is that the radiation all goes back out again. So during the night, the energy just almost all goes back out again into the sky. The difference is that you have the sun as a hot spot in a dark sky. So when the sun is there, the light comes to the sun in short wavelengths. So due to the Max Planck formula, E=h nu, that means the individual photons have much bigger energy than in the night when they go out in infrared. So you need many, many more photons to go out and many fewer photons coming in. So the energy comes in a much smaller number of degrees of freedom than it goes out. In other words, it comes in a low entropy form. That's what the plants live off. That's why we're here. It's because we get energy in a low entropy form. We send it back out in a high entropy form. Why can we do that? We can't do that because the sun is there. If the whole sky was the heat of the sun, it would be useless. We do it because the sun is hot, the sky is cold. So when you see the sun, you get the low frequency. Yes, I didn't myself mixed up. The high frequency photons coming in, and in the night, the low frequency, many, many more photons with many, many more degrees of freedom, therefore much higher entropy going away. It's because we get the energy in a low entropy form. And because we have the dark sky, we can get rid of it in a high entropy form. That's what we live off, not the energy. We live off the fact that the energy is in a low entropy form. That's the key thing. That's what Schrödinger pointed out. Now, why can we do that? Because the sun is a hot spot in the dark sky. Why is it hot spot? Oh, nuclear reactions. Blah, blah, blah. No, the main point is that gravity is holding it together. If it wasn't for gravity, you would have no sun. There would be none of this stuff. It would be useless. You're taking advantage of the fact that the uniformity in the universe was low entropy, and the entropy goes up because gravity clumps. And so you have this curious feature about gravity is that, unlike other forces on the whole, clumpy state is high entropy. Uniform state is low entropy. If it was just a gas in a box, it would be the other way around.
Yes, exactly.
What's special about the early universe is that the gravitational degrees of freedom were not activated. The universe was uniform, very, very uniform, and that's very peculiar. People didn't think of it as peculiar. They thought, well, uniform, that's what we expect or something. No, it's not. What we would expect if it was a generic state would be very, very non-uniform. That's what you get a collapsing universe would be a mess, incredible mess. You don't have that. So the huge puzzle is, why was the Big Bang so very, very special, very, very uniform? I had no idea for a long time, and I just said, okay, I used to say the Weyl curvature hypothesis. That's what I used to say. What does that mean? Well, the Weyl curvature is the curvature degrees of freedom in gravity. The rest of the curvature, you have to split the curvature into two parts. There's the Weyl part and the Ricci part. And Einstein says the Ricci part is matter, the Weyl part is the gravitational degrees. He didn't say it like that, but he should have. The Weyl part is the W-E-Y-L. That's Hermann Weyl, was a very great mathematician, and he introduced this idea of the Weyl, he didn't call it that, I expect, Weyl curvature, which is the gravitational degrees of freedom. They were not activated in the Big Bang. So I used to think, if it's quantum gravity, as everybody seemed to think, it's a very peculiar kind of quantum gravity. It's a peculiar kind where the gravitational degrees of freedom are in the beginning singularity are suppressed completely. In the end singularities are activated enormously. completely asymmetrical. And I thought, well, it's got to be a very strange quantum gravity that does that. So I puzzled about it for a long time until I originally had this thought that the universe must be extremely boring in the very remote future. You see, because I think, as you were saying, you have these black holes, and they swallow more and more. You have a galactic, so the whole galactic cluster eventually gets swallowed by one big black hole. I mean, Andromeda has this one, which is much bigger than ours. We will have a collision; it will swallow ours probably, and then other ones will swallow the whole, almost the whole cluster. Most of the cluster will be swallowed by this black hole. It sits around and it sits around. How boring that is. Sits around, Hawking evaporation takes place. It starts to reduce in size. Unbelievably boring. It takes something like 10 to the 100 years. That means not 100 years, 10 to the 100 years.
Yeah, I know.
The number of zeros is 100. More than that, I think Don Page said 10 to the 103, 109. Who cares? It's an enormous length of time. Boring, really boring. But what's more boring is when it's completely gone. You have nothing but photons, almost photons. And I thought, how boring this is. It's an eternity of boredom. But then I thought, it's pretty hard to bore a photon. When I say that, I'm not being anthropomorphic. I mean that a photon does not experience the passage of time because it travels with the speed of light. This is a relativity effect. The faster you go, the slower the time progresses, where it means that actually flashes past. If you were a photon, the whole history of the universe would flash past in an instant. And where do you go in that instant? You get to infinity. Well, when you get to infinity, people usually give up at that point. But I didn't give up at that point. You were talking about the Yabuana conference. But I actually talked at the Yabuana conference about conformal infinity. So this was, you see, if you don't have any mass like a photon, then the passage of time is not important to you. I don't know how to say this properly, but you can represent infinity as a finite boundary. I like to describe these things in terms of these Escher pictures. You have the pictures called circle limits. You know the ones I mean. There's ones with angels and devils. There's some with fish. And the whole of this universe is displayed inside this circular disk. And they seem to get smaller and smaller towards the edge. But you have to bear in mind that this is a conformal representation. Now, conformal means you know what angles are, but you don't know distances. So big and small are equivalent, but shapes have to be preserved. In the first one of these Escher pictures, you have fish with little circular eyes, and you can see they remain circular right up to the edge. Now, I'm thinking that the future boundary of our universe is like that. That there is a future boundary, which, although you wouldn't live, or I wouldn't live long enough to reach that boundary by a long shot, the photons get there, and they want to know what's on the other side. I mean, usually people say, well, there's nothing on the other side. But I got used to the idea that you might imagine there was something on the other side. And as far as massless things are concerned, what could they be? There might be something on the other side. So the view I had is, maybe it's, now here's the other part of the argument. And there I have to turn to a chap who used to be a student of mine, this is Paul Todd, who really rephrased the arguments made about how special the beginning of the universe was and put it in a different way and did some calculations on this. And I think it was a nice piece of work to say, well, you don't say that the Weyl curvature goes to zero. You say conformally, it's just a boundary. And that boundary is nice and smooth. So I was thinking, okay, let's take that. The boundary, it's the opposite way around. You see, you squash down infinity to make the future boundary, like the Escher picture. You stretch out the Big Bang to make the past boundary. It's accompanied by, if you see, the remote future will be very, very cold, very rarefied. when you squash it, accompanying by the reduction in the space distance, you have an increase in the energy. So the energy and the momentum, the temperature goes up and up as you squash it. Now, if you stretch the Big Bang, it's the opposite. The energies and the temperatures go down and down. And I thought they look rather like each other. If you could squash down infinity and stretch out the Big Bang, they're not so different. You like to think they're different, but maybe they're not so different. Now, you see, in the remote future, you have mainly photons around, so they don't really care about the scale. But what about the Big Bang? Well, it's really quite similar in a strange way, because at the Big Bang, the temperature is so big, the particles are rushing around so fast that the energy in their motion completely dominates, and the energy in their mass becomes utterly irrelevant. So as you approach the Big Bang, the particles become, in effect, with no mass. And if you have no mass, you have no measure of the scale. So this is the important thing. And it really is an important feature of the two most famous formulae of 20th century physics. What are they? Einstein's E equals mc squared, Max Planck's E equals h nu, or hf, whatever your letter for frequency is. H is a constant, C is a constant. Einstein says energy and mass are equivalent. Planck says energy and frequency are equivalent. Put them together, mass and frequency are equivalent. So that means a massive particle is a clock. It's a very fast frequency. So, but it's the basis of atomic and nuclear clocks. If you sort of harness it and you gear it down a bit, then you can produce these very nice clocks. And they depend on the fact that mass is equivalent to frequency. Now, when you have no mass, you have no frequency. You have no measure of the time. So in both ends, the argument goes, you have no mass. There's a little bit of an argument about hydrogen and things like that, but let's not go into that. No mass in the future, no mass in the past. So then it enables you to make this connection between the remote future of what I'm calling the previous eon to our eon. So I'm saying our eon begins with our Big Bang, and the end, in a certain sense, is this remote future. So you can squash down this end and join it onto the Big Bang of the next eon. Now, I used to give lectures on this, and I would think, well, nobody will ever prove me wrong, so I can go on talking about this stuff forever. And then I began to think about it a bit, and I thought, well, maybe there will be observations. And the first thing I thought about was collisions between supermassive black holes. You see, in our galactic cluster, there's our galaxy, Milky Way galaxy, and there is the Andromeda galaxy. Those are well, there's a couple of others, I think, but we are on a collision course with the Andromeda galaxy. So at some point, maybe a few thousands of millions of years, the black holes will feel each other out and spiral into each other. And okay, there will be a burst of energy in the form of gravitational waves. This will happen in a galactic cluster. It will happen probably several times. So if you take ours is quite a small galactic cluster, but take a big one, and there will be lots of these collisions, one after the other, and bang, 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 like this. You don't hear anything, but these will be gravitational wave emissions from the collisions between the black holes. These gravitational waves will, according to the theory, come through into the next eon. So the black hole collisions in the previous eon will produce signals that we might be able to see. And we might be able to see them as little disturbances in the microwave background, which would look like rings in the sky, circular rings in the sky. And you might expect to see them in concentric sets, because if there are several of these, bang, 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 as I say, there will be one ring, another ring. It's like droplets falling into a pond, and you'll get one ripple and another ripple from the same center. And so that's the sort of thing you might see. And people started to look for these things without any success, and they say, and complained that they saw nothing. But Vahe Gürsejan, who was a colleague of mine, an Armenian colleague, who took me seriously and actually did the analysis in a way which means you could look for concentric sets of rings. And he did it in such a way that you could spot these things and claim that you can see them. I may say a lot of people didn't believe us. And what was interesting, though, we were doing this, but independently, Paweł Nierowski from Warsaw, I guess, and I'm not sure if he's certainly from Poland, and he was a friend and he knew colleagues of mine. And I think he was interested in maybe testing my theory, maybe showing it was wrong or something by looking for these rings, but he didn't know how to provide a test. And I think on one occasion he ran into Christoph Meissner, another colleague, and Christoph had the idea of how you might do the test, and Paweł had the idea of what you were supposed to look for, and they got together, with other people to help them to do the numerical part of the analysis. And they had several papers in which they also saw, I should say that Vahe did see evidence for these rings, and the Polish group also. So independently, using different techniques and different methods of doing the analysis, both saw evidence for these signals. Nobody believed us. It was, when I say nobody, I mean that people who weren't actually working on the project seemed to be very skeptical and very reluctant to repeat the analysis. Some people did repeat the analysis, in fact, repeated the analysis that Vahe did on the, in fact, I was keen that they would do this because I'd like to see somebody else, see if they see the same features. They did say they see the same features, essentially the same distribution of sources, which is remarkably not uniform, which was quite strange. I didn't expect that. But it looks as though these sources were concentrated in certain regions. And they found the same thing, but they ignored this fact, thought it was not really irrelevant, not relevant. There's still some evidence, some question about that, because when you look at the Planck data, the clumping is even more evident. And we have a paper where we point this out. Nobody has commented on that as far as I know. But then, as I say, the Polish group also saw evidence for these things. But then Christoph and I got together to look for a different signal, which is what we call Hawking points. You see, we talked about the Hawking evaporation of a black hole. Now, this doesn't happen for a very long time. For the biggest ones, I said about 10 to the 100 years or longer than that. And in the conformal diagram, if you imagine the Escher picture and you look very, very close to the boundary, this effect of all that Hawking radiation will be tiny, tiny, tiny. As it comes through to the other side, you would get a concentration of all the mass that was in that galactic cluster in the Hawking evaporation, or even if there wasn't any Hawking evaporation, it would be moderately similar from this point of view, because the energy has got to go somewhere. And you can actually prove that the energy can't disappear. We're trying to write a paper at the moment, which is, well, I won't talk to you about that because we haven't finished it. But you can actually see how much energy will come through into the next eon. And if this theory is right. But what we saw in a paper which was published over a year and a half ago in the monthly notices of the Royal Astronomical Society, a very respectable, distinguished paper, distinguished journal, I should say. This paper was accepted and published by them. And we claim to see these, what I call Hawking points, or Hawking spots, because you don't actually see the little point. Because as I said before, you have to wait 380,000 years before you actually see the radiation. So what is a little spot in the crossover into the next eon spreads out to a region which apparently is about 8 times the diameter of a full moon. So if you look at the evidence, which we do see spots which are 8 times the diameter of the full moon. And whether that is the right figure for the actual expansion is now a slightly contentious issue, so I don't want to go into that. But you certainly see spots of that size. And we see the analysis that Christoph produced says that there is a confidence level that we have of the existence of these spots of 99.98%. So we are 99.98% confident, according to this analysis, that these spots are there. That confidence does not transfer to the actual location of these spots. But the location of these spots, I don't know whether you can trust all of them, but let's say the strongest 5 that we see in the Planck data, that's the most recent satellite. Well, there's now another satellite, but the Planck satellite was the most recent and most detailed analysis of the microwave background. And if you look at the 5 strongest spots, and then you look at the WMAP data, that's the earlier satellite, and you see that these 5 spots are in exactly the same places in the WMAP data also. Not only that, but there's another spot in the WMAP data, a 6th spot, and we look back in the Planck data and it's there too. So they're there, those 6 points, I'm calling them Hawking spots, well, the centers of these little spots, which are 8 times the diameter of the moon. You look at the center, those centers are in the same places in both satellites, those 6 spots. So I'm saying those 6 spots are probably genuine Hawking points, and therefore they are probably the result, I'm claiming this, of a previous eon cluster of galaxies. And nobody, as far as I'm aware, nobody has made any comment on that paper. People have made comments on an earlier paper that was put on the web, and they kind of refer to this paper, but it was not that paper. The paper that was published, maybe there has been a commentary on it, but I haven't seen one. I have seen some commentaries on the one which was put on the web, which is not actually the paper that was published. And the comments I've made, they try to poo-poo the analysis, I think, somewhat. I'm not quite sure. Reduce the probability that we see. I think by doing the analysis a different way, which I can't see why they want to do it a different way. One of the groups who saw it actually do see the same spots. They don't sort of claim to see it. It's quite strange. Never mind. There's a lot of reluctance to accept these things as real. This book is more recent. No. What is this book? It's Fashion, Faith, and Fantasy. It does mention the theory, yes.
Okay. So this is the Polish version. And yes, the title is intriguing.
Yes.
The title is intriguing.
The publishers did not want that title. They kept trying to make me change it.
So tell me, how do fashion, faith, and fantasy influence science, the scientific community? Yes. And what does it mean that a given theory, a scientific theory, is or is not beautiful or elegant?
That's a tricky one. You see, like many physicists, I'm very impressed by the elegance of a theory. So, well, there's a lot of elegance in the Newtonian theory and the beautiful work that, well, Kepler and Galileo and Einstein and Newton in working out the elliptical. That's very, very beautiful in that. But then you take Einstein's general theory of relativity, which has an enormous elegance about it. But we can't trust the elegance, because you can find a theory which may be very elegant, but it's not true. There is, I think, something when it is true that gives it something special extra, but it's hard to pin that down, very hard to pin that down. I mean, quantum mechanics has its elegance. It has an elegance, and it has something. Yes, I should explain what the 3 theories I was talking about here are. You see, I gave 3 lectures in Princeton. One was called Fashion, one was called Faith, and one was called Fantasy. And I'm not sure whether they were happy with the title, I'm not sure. But when I decided to make it into a book, or the book was supposed to be part of the 3 lectures, the publishers kept wanting me to change the title. But I didn't want to change the title, so they eventually agreed. But I should explain, the fashion was aimed primarily at string theory. You see, string theory is very still fashionable as a theory of quantum gravity. Okay, it has a lot of very elegant mathematics, and I agree with that. So a lot of the mathematics is extremely elegant, and it has a beauty. But you shouldn't be driven too much by the beauty. The trouble is, to me, it's not so elegant because it only works when you have the wrong number of dimensions of space. Now, you see, the original form of string theory, when I had it described to me, I found it very, very elegant. But then when they decided, oh, it doesn't work with 3 space dimensions, you need, first of all, 25 space dimensions, 1 time dimension. I thought, ugh, that's not very nice. It may be elegant, but it's not physics. They say, oh, well, the extra dimensions are squashed into some tiny, well, no, I don't. I have reasons for not believing in that. Then it got down to 10, or 10 and 26 at the same time, which is always very puzzling to me. Not even elegant, I thought. But anyway, that was the fashion, because many people were working quantum gravity. By far, the majority of people working in quantum gravity were working in string theory. But I did not find it particularly elegant because of the way that you had to struggle to make it look like physics, ordinary physics, because the number of dimensions of space. Most of them are supposed to be tucked into a little tiny space, and I didn't think that worked because you can't trap them there. They leak out, and let me not go into it. But I had problems with that. What is the faith? You see, I should say these are actually very big fish. Fashion was a big fish because this was the predominant theory of quantum gravity. Faith is an even bigger fish. What is the faith? The faith is in quantum mechanics at all levels. Now, you see, quantum mechanics, unlike string theory, has an enormous amount of experimental support.
Yes.
Huge amounts of support. And it has many, many things which were simply inexplicable on classical theory. So there's clearly a lot of truth in quantum theory, no doubt about that. However, this leads one to have a faith that this theory is true at all levels, not just for little tiny things, but for big things. And yes, because it works so well for little tiny things, I think the argument is, roughly speaking, big things are made of little things. So if you have a good theory of little things, it'll tell you what big things do. That's maybe a simplification of what people think, but there is something like that. And my argument is, no, that's not right. And there are reasons for thinking this is not quantum gravity. You see, usually people think of combining general relativity with quantum mechanics is looking at very, very tiny dimensions where 20 orders of magnitude smaller than an elementary one. So you have to look at 20 number with 20 zeros smaller than the particle. Okay, maybe that's right. I'm not arguing against that. But what I am arguing against is that is ridiculous if you're looking for experimental support. You have to have an accelerator, which is absolutely absurd, and we're nowhere near that. However, that's not the main interplay between general relativity and quantum mechanics, according to me. The main play is the other way around. How does general relativity theory affect quantum mechanics? And the reason that that's important is that quantum mechanics has one huge flaw. And why I was arguing in this book about the faith is that people don't see the flaw. And the flaw has been there right from the beginning of the theory. What does the theory say? Well, let's take the Schrödinger equation. Wonderful equation. Tells you how a system evolves in time. You have d by dt, blah, 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 blah. Tells you how the system changes. If you know the state now, it tells you what the state will be tomorrow and the day after tomorrow. However, that's not what you see. What do you see? Well, you change your mind about what you're looking for. You say you make a measurement. You make a measurement on the system. And when you make a measurement on the system, you violate the Schrödinger equation. you don't do the Schrödinger equation. You do something else, which is called making a measurement. So quantum mechanics has two parts to it. One is the Schrödinger equation, or evolution, or whatever, however you describe it, Heisenberg evolution or something, but the Schrödinger equation. The other part is the measurement process. The measurement process is in blatant contradiction with the Schrödinger equation. You say, well, you have your state, it's evolved, and you want to look at it. Well, how do you look at it? Well, you wheel out of the cupboard your measuring device. The measuring device measures it. You wheel it back into the cupboard, and you've now got a new state with probabilities. It says it's this or this or this with certain probabilities. But you've cheated, because you shouldn't wheel the magic thing out of the cupboard. You should apply the Schrödinger equation to the machine too.
Mm-hmm.
And if you apply the Schrödinger equation to the measuring device, it doesn't measure anything. It just follows the Schrödinger equation. It doesn't give you what happens. There is a thing called the collapse of the wave function. Now, the collapse of the wave function, nobody would understands, or nobody still understands, I would say. I thought it was due to gravity. I have an argument, you see, which says when gravity becomes important in the thing, then you cannot follow the Schrödinger equation. There is an inconsistency. There's an inconsistency between the evolution according to the Schrödinger equation, or if you like, the main thing is the superposition principle, which says that if A can happen and if B can happen, then you have states which both happen at the same time. And that's very much part of quantum mechanics. And what I'm saying is that that principle is inconsistent with the principle of equivalence. Principle of equivalence is the basis of general relativity. Well, that goes back to Galileo. That's him imagining a big rock and a little rock falling from the leaning tower, and they fall together. You can cancel gravity by falling freely. That's the observation made by Galileo. Well, theoretical observation. But he made experiments too, with things rolling down. No, it was an amazing thing. And Einstein picked up on that and developed general relativity based on this basic principle due to Galileo. Now, people sort of forget this basic principle. In quantum mechanics, it's inconsistent with that principle. That's what I'm saying. If you look at the mathematics of superposition principle in quantum mechanics, you see it is inconsistent with the principle of equivalence. And this argues to me that there is something wrong with quantum mechanics which is corrected by general relativity. This is not yet tested experimentally. It's not so far, though. You see, where is to test the strings or whatever it is, you need accelerators which are way off the picture. These are experiments which I hope will be done within the next 5 or 10 years. They're doable now. Nobody's done them yet. There was an attempt to do this by Dirk Baumeister, and I hope he will succeed eventually. He's been slightly thrown off course by, I think, trying to get things cold enough. But maybe that experiment, or maybe some others, which I'm interested in collaborating with people on. And I hope that they will be done while I'm still alive, which is not certain, but I hope so.
It's really fascinating. A lot to learn, still a lot to observe, still a lot to discover.
Yes, indeed. Yeah.
Well, actually, I wanted to ask you, before we finish, how did you become interested in science, knowing you come from a family with scientific and artistic traditions? But actually, I don't think I have to, because obviously you are like a person whose creativity, ingenuity never ends. And was there anyone who actually had to inspire you to
well, there was.
To fulfill this endless curiosity you have about the world, about how the world works?
There's no question who that came from. That was my father.
Mm-hmm.
My father, I mean, he had his faults, I must say, but he did have an enormous enjoyment about science and puzzles, things like that, and chess. Well, you said that was my younger brother who became British chess champion 10 times on record. But I was not interested in chess, fortunately. He was much too good so that I never was even tempted to play chess. However, I did have lots of discussions with my father about science. And we used to go for long walks, and he would talk about the plants. He was a biologist, really. I mean, he was more interested in biology. Mental deficiency was the sort of problems he had, problems he was interested in.
Mm-hmm.
And he studied problems of people who had problems with the brain, one way or another. But and inheritance was the main, how such diseases could be inherited.
Mm-hmm.
So genetics was, but there was a lot of statistics in what he did. So he had a lot of understanding of mathematics, but he was interested in mathematics for its own sake. There's no question. It was not just to do statistics. And I certainly learned a lot, I think, when I was at school in Canada during the war years, and we used to make polyhedra together. But I did other things with, he just inspired, I think it was the playfulness with regard to mathematics, and the thing that mathematics could be fun. I think that I got from him very much. And it's a shame he died before I produced the non-periodic tilings, because it would have enormously excited him. There's no question about that. The impossible figures he did, that was partly developed in conjunction with him. So that those things were things that I did with him. So I wrote 3 papers with him, actually. Was it 3? I think so. 3 or 4, yeah. So, but it was, I think, that science and mathematics could be fun. I think that was what I got from him, and is fun.
It is fun.
Yes.
And when you are talking about it, it's much more fun. I think it becomes so much more exciting and fascinating, and makes everyone want to fathom, to learn more and more and more about it.
No, I think it should be made to be fun, not just dreary. I think that's the point. You're absolutely right. It's well, there are some of my lectures made it pretty dreary. I remember that, some of the lecturers I went to. Some made it fun, some didn't. But on the whole, the ones that made it fun were the ones that inspired me the most. That's true. Yeah.
Professor, thank you so much. It's been such a pleasure and such an inspiring conversation I had with you.
Well, thank you. It's been great fun talking to you.
Thank you for accepting my invitation. Thank you for joining me today. Well, I don't know. I'm really speechless for now, because I have got so much energy from you. Not only information, fascinating information. You've shared your knowledge with me, and of course all the people who will be watching us. But also, you've also given me so much energy and,
well, I hope so.
And things to think about.
Okay, well, I'm glad to hear that. Thank you very much.